So for this one, this is going to be basicity. And when we talk about basicity, we're really kind of focusing on the nitrogen lone pairs in all of these. Right? So we're going to compare across things. And really, this basicity is honing in on the factor of resonance and how that affects the reactivity of a base, how reactive a base is. So if you look at this first one, you have aniline and cyclohexylamine. So what's different here? Right? So which one of these is more reactive? So if I make A and B. Excellent. So B is the more reactive base. Now why is that? It's because B cannot do resonance. Right? In this case, resonance would have this lone pair going into the ring and making it, right, spreading that charge out would make it less reactive. So resonance, not always, in this case, makes this one more reactive because it can't do resonance. Right? Now what about these two? So now A and B again. Which one of these would you propose as the more reactive one, A or B? So this one's a little different. So obviously both of these nitrogens can do resonance. So the question is, how is this O-methyl group affecting it? Now here in this one, it's in the para position. Here it's in the meta position. So the only way to know at this point is either just memorize it or to be able to draw some resonance structures. So what you're going to want to do is draw resonance structures with this oxygen. All right? So if I bring this into the ring, what kind of resonance structures do I form? Now remember, when we're doing this, what we want to have happen, right? We want to have the lone pair on this nitrogen, or just this nitrogen, right, be more electron rich. That's going to make it more reactive, more basic, right? So let's keep moving these lone pairs around. Resonance arrow. Balancing my charge. Okay. Now this seems good because I have a negative charge right next to that nitrogen. That means I'm pushing electrons towards that. It's really close to that. That's good. What about in this case? Does that happen with this one? So take a couple seconds and see if you can draw out the resonance form for this. All right, so I've drawn out some resonance forms when this electron donating group, right? Anything with a lone pair next to the ring is an electron donating group, except for the halogens, fluorine, chlorine, bromine, and iodine. So this oxygen donates electrons in when it's in this meta position, but does it ever get to a point where we have the electrons on the carbon attached to the nitrogen? No. So actually this A makes a more reactive base, a more reactive nitrogen in this case. All right, so the substitution on the ring matters because resonance matters, right? The only way you're going to know that is by drawing some resonance structures. So now let's change it around a bit. So now instead of having an electron donating group, a group that pushes electron density into the ring, let's have an electron withdrawing group. So in this case, this ketone, right, this carbon of the ketone is electron withdrawing, right, because it's double bonded to an oxygen. So it's going to pull electrons out of the ring. So instead of pushing them in, it's going to take them out. So let's see which one of these, right, if you had to guess, so I said A or B, which one of these is going to be the more reactive base now? So let's draw some resonance forms for B. So since it's electron withdrawing, we're taking electrons out of the ring. So there's a plus charge in the ring, right? Electrons left the ring withdrawn. Oh, wow. So it's just kind of just the opposite, right? If you put a plus charge next to the nitrogen, what's that nitrogen going to do? Well, it's going to say, hey, I have a lone pair. I want to stabilize this, right? Because what kind of resonance form do we make now, right? We made a really good resonance form. Why is this resonance structure better than all the others? Why is this one the best one I've drawn so far for these ones? Because of the, what's the one rule to rule them all? Oh, okay. Turn the sound on. So do we see that right? So this is actually pinning up the lone pair in such a way that now it's being involved with this resonance form. If this lone pair, the nitrogen, is involved with the resonance, is it going to be able to react out here with an acid? No. So that's why this is less reactive, right? Because it's going to be willing to help out. If you draw the resonance forms for this, you'll see the nitrogen is not directly able to help like it is here, right? There will not be a plus charge right there like there is here when it's in the pair position.